It's my pleasure to introduce our today's speaker, Michael Lacey from Georgia Tech.
Thank you. I've been occupied with this topic for the last year, but this is actually the first time I'm using transparencies to speak about it, so there'll be a few typos. It is not as closely related as it could be to the topics of this particular theme at the Newton Institute, but very beautiful topic. And in particular, for experts in the subject would instinctively know that there were two giants lurking behind the scenes, Jean Bourgain and Elias Stein, who both passed away recently. And so their influence is very strong throughout the entire talk, though I won't be able to, I won't point out every entry that these people have had in the subject. But of course, Elias Stein's closely associated with fine properties of spherical averages. So he's already making first observations back this even in the 1960s. So I want to recall some results in the continuous case. So we take a function, a priori a smooth function, and we form an average over a ball of radius r. To begin with, we can take r to be 1. So in particular, you have a lower dimensional surface. And particularly relevant is the fact that the Fourier transform has a decay, though somewhat substantially smaller than a typical average. So this, in dimension 1, this formula is meaningless, of course. And in dimension 2, you have half square root decay. And in dimension 3, you have a full -1 decay. So in dimension 2, the averages sort of gain a half derivative, but in dimension 3, a full derivative. Moreover, there is this, the Fourier transform is explicitly given in terms of a Bessel function, and there is this oscillatory behavior, which is another feature of the averages that implicitly comes up. Now this is a very pretty result from 1971, and so I'm sort of asking a little indulgence to recall such a property from 1971, but I'm phrasing it in a slightly different way. If you average over the entire ball, you take an integrable function, of course you get an L infinity function. But if you integrate over a sphere, you cannot hope for such a good result. And the sharp result is actually a reflection of that decay that I just pointed out in the previous slide. And the LP improving property is that it is, in more conventional notation, is that if I average over sphere radius 1 and I take a function that's locally an LD plus 1 over D, then it's an LD plus 1. Again, locally. And these are conjugate indices. And I phrase it this way for other reasons. And now Stein is, of course, very famous for his work on the full supremum, not over just a fixed radius, but you take the full supremum, and it's somewhat surprising that it took until the thesis of Wilhelm Schlag that one concentrated on, again, a localized maximal operator. So you don't soup over all radii, but only the radii from 1 to 2, say. And again, there is an LP improving property, and it's more complicated. First of all, the critical index drops from the d plus 1 over d to d over d minus 1, and so now the harmonic analysts will feel more comfortable because they'll recognize the exponent d over d minus 1 as coming from Stein's observations. And then, because this is non-convolution, I don't get a triangle, but rather I get there. It turns out that the sharp answer is this funny four-sided figure, and there's a little bump from the diagonal coming from the Strickhart's estimate. Now, the more familiar properties about the Stein maximal inequality actually follow from this and more. Because sparse bounds hold for the triangles that I've just illustrated to you. Now, I'm not recalling sparse bounds for this audience. It would require a couple more slides, a little extra intellectual baggage. So I'm not recalling the sparse bounds. We'll focus on the local estimates, and let me suggest that those are the critical things that then imply some very interesting facts for the Stein maximal operator here and the Lacunary spherical maximal operator. And the sparse bounds are in the first hand, they're sort of a funny nonlinear bound for maximal functions. And the second, they're actually the natural extension of the LP improving inequalities. You take the proofs for the LP inequalities and they naturally give you the sparse bounds. And the sparse bounds are in fact essential improvements over the LP improving. And then once you have them, you can deduce weighted estimates and vector valued estimates for the corresponding operators that are the strongest known. This was a particular motivation for the topic that comes next, where no weighted inequalities were previously known. Right, so there is a slightly deeper theory. As I said, it requires a little more baggage, so I'm chose to not include it for this talk. So what I've been concerned with is extending these beautiful results of Stein and Littman and Strickhart's to discrete averages. Again, a topic that Eli Stein was deeply involved with. Now, this is not, so we're going to take sum over f is about a function on the integers, n is a point in the d-dimensional integer lattice, and you add this up, and this is an approximate normalization, so it's more or less an average. Now, the picture is just for illustration. It's actually not an integer sphere. It's its points equally distributed according to some potential, of which there's many, many pictures on the internet, and apparently none for the integer sphere. Now, in the continuous case, when you average over a sphere, it's intuitive that you lose one dimension. Didn't even comment on it. In the integer case, you lose two. Which is counterintuitive, but the rationale for that is right here. If you take this annulus, think of lambda as 100 or 1,000, and you look at this annulus, it's manifest that there are about lambda to the d lattice points inside that annulus. Now the next thing you have to ask is how many integer sphere radii are there? And there's lambda squared radii. There's lambda squared numbers whose squares are integers. Now, the last thing, now we know from Jacobi that every integer is the sum of 4 squares, but it turns out that in dimension 4, it's barely true in the sense that there are arbitrarily large integers which have only a few representations as a sum of 4 squares. But if we go to dimension 5, then the integers don't care any longer. Every integer sphere gets the right number of lattice points. So you lose dimension 2. And there should be an F there. There'll be a few other typos. Now, of course, one of Eli Stein's famous works also involving Ákos Magyar and Steve Wenger, involve the discrete version of the Stein maximal function. But the results that I'm talking about will extend their work in interesting ways. Now, there's another complication that comes about. Again, it's a complication which I didn't even mention in the continuous case. The complication in the integer case is not all radii are the same. If you take radii of different values and you look at the integer points on the sphere, there are very subtle and important distinctions in how those lattice points are arranged on the sphere. So, nevertheless, we're interested in sort of scale-free bounds. And so what we're going to look at is have some sort of operator, a spherical average, say, and we're going to think of f, it acts on functions supported on a cube E of side length lambda. And so we're going to take this inner product and normalize so it's like we're taking an inner product in a normalized probability space, and we're going to compare to normalized LR and LS norms. Right? So this addresses the fact that the integer spheres are different fundamentally as you pass from one radius to another. And now, last of all, we're sort of the beautiful subject of discrete harmonic analysis created by Bourgain in the mid-1980s, is building up some kind of dictionary to pass from one operator to the other. Now, typically, this has been operators mapping LP to LP. And the new direction that I've been addressing over the past year is these LP improving style estimates. So there is in the LP to LP, there's a kind of, we now have nearly 40 years of a rather elaborate dictionary that's been built up, but in the LP to LQ, it's only just been started. And so, in the setting of spherical averages, you can have the fixed radius, and now this is a typo That's not d plus, that should be d plus 1 over d. This is the Littman exponent. And now, as I'll illustrate to you, in the continuous case, we don't, I would not say the situation's resolved, but there's a different exponent. Here, d plus 1 over d kind of differs by 1, which is a reflection of the fact that the sphere is codimension 1 in the continuous case. And here, the exponents differ by 2. Moreover, there's an arithmetic feature. In the Lacunary case, the Lacunary spherical maximal operator, I didn't recall it in the continuous case, but it's a well-known thing. It's bounded on the LP to LP for all P. And the situation in the discrete case is complicated. There's different results, and there's not yet an overarching story on that line. For the full supremum, I'm principally focused on the funny four-sided figure that came out of Wilhelm Schlag's thesis. And we now have a very pretty variant of this in the discrete setting. It would seem to be complete, but we certainly don't have a proof that it's complete. So the fixed radius case, this is due independently to Robert Kesler and myself and Kevin Hughes. Again, there is a interesting, for simplicity, I'm sticking to the case d bigger than 5 because there's a little complication at d equals 4. And you take cubes of side length lambda, where lambda is the root of an integer. F is supported on E. And now if you take this local LP prime norm, this is less than the local LP norm, provided P, well, the 2 case is trivial because it's just an average, and it's absolute constant by Cauchy-Schwarz. But the interesting thing is that as P degenerates, it's still true. However, there is an arithmetic aspect. The constant can depend upon the number of distinct prime factors of lambda squared. So if lambda squared is the power of a pure prime, it's an absolute constant. We also have bound. We know that the constant can be taken absolute, but then we even know a stronger result. So I don't state it that way. Because now I'm considering the local maximal function. So in the continuous case, that was a supremum over radii from 1 to 2. In the discrete case, you have to change its definition. It comes up in the next transparency. But you have to take a supremum over comparable radii with an additional parameter. And now R1 and R2 are the Schlag exponents. So these are the Schlag exponents right here. And now you draw this dotted line from 1/2, 1/2 up through the Schlag exponent right there, which is on the diagonal. So it continues through 1, 1. You take a particular linear combination, which is d minus 4 over d 4 over d of r1 and a half 1/2, and you get a new point, call it z1, and that's one corner of the diagram. But you get to do the same thing at R2, which is the Strickhart's point. And there's another Z2 with the same linear combination. Now this point is actually not horribly difficult, but the other one is. The other one takes a significant elaboration to get. And the inequality is that provided 1 over r and 1 over s are inside this figure, you get this version of the LP improving in the discrete case. And moreover, the sparse bounds hold in these exponents, and then the sparse bounds give you vector-valued versions of the discrete Magyar-Steinwanger maximal function. So, these things are very pretty, and now I'm going to, for the fixed radius case, I'll sort of quickly outline the proof. This may be kind of a short lecture, by the way. And I'm going to illustrate, and this illustrates the proof strategy, which I call the Michelle-Obama proof strategy. Michelle Obama has a line in one of her political speeches: when they go low, we go high. But in this proof strategy, you go high or you go low. You have no one or the other. And this, of course, is a very there's a very beautiful story behind this picture, and that's the portrait, the official portrait of Michelle Obama in the National Portrait Gallery in Washington, D.C. Right, so you go high or you go low. The strategy actually goes back, as many elements of the talk, to Bourgain, and further elaboration by Ionescu. So the fixed radius case, so the discrete version of the Littman inequality, where d plus 1 over d minus 1 is the crucial exponent. The strategy is this. Okay, so the epsilon is a nuisance parameter, but for all integers n and for all radii, lambda squared, and a cube which we can take to be centered at the origin of radius lambda, and f is a subset of the cube. You take this average, this spherical average of f, and you'd write it as two pieces, m1 and m2. m1 is the low frequency part, and on it you have L infinity on this and L1 on that. So this is the upper endpoint of LP improving. This is the version of LP improving that you wish were true. That is true for the usual averages, except you lose an n squared. And then the other is the L2 estimate, which we know is true, but with a gain. So L2 and L2 with a big gain and an arithmetic feature.
So what is this n? This is the
n. You tell me n, and I produce m1 and m2. N is.
But you produce by cutting frequencies. Some sort.
You're cutting into high and low, but high and low take a range of possible definitions. And so now this is right. This is a decomposition which holds for all integers and for all lambda. So then you take this information and you optimize. And it's most convenient to do so in a Lorentz space setting, but it's just noodling around once you have this. Now this is extraordinarily convenient proof strategy to use because the Hardy-Littlewood circle method is about to kick in and is going to give us a rather complicated decomposition of A lambda. And in this decomposition, you just have to use a sorting hat. One goes low, each element either goes low or high. That's all. So this is a sort of a cartoon of the decomposition. So A lambda, we're going to use the Hardy-Littlewood circle method to decompose into major and minor arcs. I don't expect that you know what those terms mean. As part of the beauty of the subject, makes it extremely interesting because it's kind of inherently multi-scale. The minor arcs is going to be high. The major arcs is which is where the multiplier, where A lambda is most structured. It is going to have fractional denominators. It's going to have fractions in it. If the fractions have a large denominator, it's going to be high frequency. Which means that you'll have the major arcs where things are rather structured, but you have a small denominator, and then you need to do a further Fourier splitting into low and high. So this is a preparation for the next slide. I think the next slide is by far the most complicated. Is that yeah, it's by far the most complicated. The beautiful feature identified by Hardy-Littlewood and Bourgain taught us how to exploit it in analysis is that you take these number theoretic averages. Now this is simply a convolution. So it's expressible in the Fourier transform. And now this Fourier transform is going to have several copies, many copies of a spherical average. So the A lambda is the multiplier, and it's going to be the sum of the major and the minor arc. Now the minor arc is the part where the frequency variable xi is very far from rational, and this will make everything very small, though it's not necessarily easy to prove that fact. The major arc piece is the component of the multiplier that is close to being rational. And so Q is going to be the denominator, and the Q's are going to have to range from 1 up to lambda. And now, again, it's so you fix a Q. And now the multiplier is going to be on a 1 over Q lattice, and around each one of these lattice points, I thought I would make a picture of this. You're going to have a little copy of the continuous spherical average. So L is in ZQ to the D, and here's L over Q, which is sitting inside the torus, and here is the Fourier transform of the continuous spherical average of radius lambda, and it's translated. So there's a certain periodization of it that lands up at each one of these points. And the periodization, and this is simply a cutoff function, so that the phi is just a cutoff function to localize around each rational point. And then finally, you get a certain weight. So we see the continuous spherical average sitting right here at each rational point. And then there's a weight sitting here, and inside the weight is another discrete copy of the spherical average. But however, this is somewhat hidden. It's hidden inside of a complete Gauss sum with a further, where the complete Gauss sum is the classical quadratic Gauss sum. And it has this further complex weight where e to the q is 2 pi I theta over q. And this is the multiplicative group. Z mod q. So a q is 1. And now the q to the negative d normalizes all of this. And it's not, I wouldn't expect you to know this, and it's not totally obvious, but this is actually a Kloosterman sum. Very beautiful. And so you see many copies of the same problem on many different scales.
Is it Q prime?
No, sum over all integers. Q less than lambda. Right? Each rational point, not the prime rational points. Now, of course, here we know basically everything about this guy, and for the fixed radius case, the only thing that we need to know is the rate of decay. The oscillatory feature is not relevant to us. So that's totally fine. So this part, we'll certainly can guess high-low components there. But now the Kloosterman sum, of course, is, as I said, as I'm trying to stress, is a discrete variant of the spherical average. It's a spherical average happening on ZQ to the D. And it satisfies a very beautiful, very profound estimate of André Weil from 1950-something. A corollary of his deep work in algebraic geometry is a quantitative estimate. The Kloosterman sums, that should be a Q. That lambda should be a Q. I said there was a few typos. That's one. That should be a Q. There's no lambda involved. Q to the 1 minus d over 2. Now d over 2 is what you get from the classical quadratic Gauss sum. And now the Kloosterman has a sum over the multiplicative group, morally Q elements. So what this represents is a square root of Q gain over the Gauss sum estimate. Except it has a certain multiplicative thing in it. The multiplicative thing is you have to take lambda squared, you take out its even factor, and then you write the odd factor as the thing that is relatively prime with respect to lambda squared, and then you take the even factor times the remaining thing, the remaining factor with lambda squared, and take square root. So this is can be as big as another square root of q, meaning that the trivial Gauss sum bound is optimal. However, that is infrequent. It's infrequently big. And Magyar tells us that Ákos Magyar tells us that the minor arc term is indeed very small. So it is the row that contributes the arithmetic feature of the estimate. And so now I will just have it's heavy liftings over. I'm just going to sort of quickly highlight what you have the sorting into high and low frequency. So you have the A lambda of f. And now remember, in the estimate that we want to, our sorting is done relative to an auxiliary integer n, which is allowed to vary. So if the radius is small relative to n, everything goes into low. It's just swept into low. Proof stops. So the interesting case is when lambda is big relative to n, and then you have to go to the circle method. And the minor arc term is clearly going to be a high component. Magyar gives us a very good L infinity norm on the Fourier transform of the minor arc component, so we just use Plancherel, we're done. And now if the denominator is big relative to n, we're simply going to use the Weil estimates and sum, and that's just going to be a high pass. So that leaves the case where the denominators are small relative to n, and that obviously requires a supplementary estimate. And so the supplementary estimate is kind of easy to guess. You should take the spherical average and you should smear it out. There's a little noodling around about exactly how that should be done, but it's what you're going to do is you want to change the spherical average to something that you can compare to a typical average. Well, that can only be done by smearing out the annulus. How wide should you smear it? Well, this should be lambda q over n. Remember that q is less than n. And then as soon as you do this, you can make a comparison to the ordinary average. Obviously, you're going to lose in n and q, but that's allowed. And you choose this ratio to balance out the Weil estimates. So you do this, so you smear out the annulus, the circle average to an annulus average, and that's going to be the low pass part. And then you do the high pass part. And here you simply rely on the decay of the Fourier transform, which was slide 2 or 3. Well, there's actually an extra trick. In the low pass part, in the real variable part, you have an average over an annulus, which can be paired, which is just an average of f. But now you can compute the kernel on the low pass part explicitly, and another miraculous exponential sum comes up. The sum of Ramanujan. which are distinguished among many exponential sums by having vastly more than square root cancellation, though in this context we just need the trivial bound that this is at most q squared.
Is A.
What? Oh, there's another typo, thank you. There should be a multiplying by both. The Ramanujan sum is a sum over the multiplicative group of a times a frequency. Well, that's I thought it would end early, and certainly there's there's much more that can be said, but I will have to leave that to other seminars. Thank you.
Thank you very much. Any questions?
So if you take the sup in lambda, what would be the main difficult? I mean, clearly it will be more difficult, right? For fixed
actually, the high level for the sup over lambda, the high level part of the argument is the same as this slide, except here the argument goes far deeper. You need fine properties of the Ramanujan sums.
You need to use the oscillating part of the.
And you need, right, but you need to use the oscillating part, but fortunately there's a way of the Fourier transform of d sigma, but fortunately there's kind of a black box way to exploit that fact. So it's not, the novel part is the much finer decomposition that takes place on this part, splitting it into many more low pass and high pass components. It's a much harder argument. Another very interesting question is, I mean, the sharpness in the continuous case is well known, but sharpness in the discrete case seems impenetrable. Sharpness boils down to what's interesting about these things is that the inequalities give you very remarkable inequalities concerning the number of solutions to certain systems of Diophantine equations. So the sharpness would seem to go the other way round, and that's notoriously difficult, subject to number theory.
Questions? Not let's think, Mike.
I think.
Oh, sorry.
So you have this number theoretic constant involved. Do you know if some kind of this constant is necessary?
Oh, absolutely not. That speaks to sharpness,
Okay.
and really don't know.
So you don't even know if there is some influence of the number.
No, absolutely not. It would, and I think my next paper I might have to formulate another conjecture about Kloosterman sums in order to try to push it further.
All right. So, thank you very much.